Okay, so in this example, we're told that we have a pin P, which is constrained to move along an elliptical ring, whose shape is given by x squared over a squared plus y squared over b squared is equal to 1. X and y we're told are given in millimeters, and we're furthermore told that the pin is constrained to move within a horizontal slot that is moving upward with a constant speed of v. In this problem, we're asked to determine the velocity and acceleration of the pin at a given position, and to use the parameters given in the problem. Okay, so the way we're going to help ourselves out here is we're first of all going to identify that this is a Cartesian problem and that we have unit vectors already nicely sketched in here, and so we'll use I and j unit vectors conventionally. And if we do so, we can note then that the velocity in this problem is going to be given by x dot in the I direction, excuse me, that was bad notation there on my part. Let me try again, x dot in the I direction plus y dot in the j direction. And similarly, the acceleration is going to be given by x double dot in the I direction plus y double dot in the j direction. And so given that we know a little bit of information in this problem, we're going to see that these are relatively straightforward to compute. Namely here, what we know is that because the point P is constrained to move within this horizontal slot which is moving vertically, that y dot is going to equal that vertical speed v. And because that vertical speed v is constant, we'll have that y double dot is equal to 0. What we need to do then to solve this problem is to identify values for x dot and x double dot. And the way I'm going to do that is through implicit differentiation. I know, due to the elliptical shape, that x squared divided by a squared plus y squared over b squared is equal to 1. If I implicitly differentiate this equation, what I'll have is that 2 times x dot divided by a squared plus 2 times y dot divided by b squared is equal to 0. This, of course, is obtained by taking the time derivative of the expression for the ellipse. I can go ahead and clean this up a little bit, and if I do so, I can cross multiply, and what I'll see here is that this expression is equivalent to 2 times x dot times x times b squared plus 2 times y dot times a squared is equal to 0. Or, dropping the 2's, x times x dot b squared plus y dot b squared, excuse me, a squared is equal to 0. We can plug in numerical values here for y dot, a, and b, and note that we can solve for the numerical value for x from the expression up above, and I can get from here x dot. That's a numerical exercise, so I'll leave it for you to do. Instead, what I'm going to do is I'm going to work on trying to find x double dot. And so what I'm going to do is I'll take the time derivative of this new expression here. And so if I do that, what I'll have, using in this case the product rule of differentiation, I'll have x dot, the time derivative of the x term, times another x dot times b squared, plus x times the time derivative of the second part, the x dot term, which would be x double dot times b squared, plus y dot squared a squared, plus y times y double dot times a squared is equal to 0. Again, we can note here that we know that y double dot is identically 0, and so I can cross out this term. I have numerical values for a, y dot, x dot, b, and x, and so I can use this and solve for x double dot. Once I have both x dot and x double dot, I can come back to these expressions I previously developed for the velocity and acceleration of point P, which I'm highlighting here for you now, and if I plug in those numerical values, I'll have the numerical answers for this problem. I'll leave it up to you to do the numerics. I know you can do it. Best of luck.